Oh, yeah, right. Yeah, in 3D, you can't really use that.
Using the unit,
Yep,
like you just make the vector and then unit v it in the calculator.
exactly. Okay, so we are on rigid body statics. You guys might be starting to figure out the trick where if you ask enough homework questions, we don't get far enough for me to assign more homework questions.
Isn't it? I thought you planned all these that we get homework all the time, except before tests.
Rob, question: how 3D do you want our like?
Your free body diagrams?
Yeah.
I don't really care. I mean, I sort of try to roughly do the outline the way it's drawn in the picture, but um,
It's a little different.
it is. Okay. So we got this thing. And one thing that you have to notice about this is that the cable that goes from I to C to F to H, that's all one single cable. So that's just going to be one cable tension. Okay. It's just going through pulleys. And then G and E is a separate one. G to E is a separate one. Okay, so let's first come up with all the just the coordinates of all these points. And one thing,
It's in inches, right?
it is in inches, and we can do these calculations with those distances in inches. That's fine. You know, your first thought might be like, oh, I'm going to convert all these to meters, and that would work fine, but we can just keep them in inches too.
Would the final answer be like in inches then?
Well, if you had any couples or anything that you were trying to solve for, then yes, it would be. But this is just forces, so that's not going to come up.
Right, but then once you get a different answer, if you use meters or no?
No, you'd get the same answers because it just all ends up being ratios of moment arms.
Oh.
Yep.
Could the rope, like if you tied the rope from G to E to the other rope, would they all the tensions still be the same? You have a third arm of the rope.
It would change the angles of things for one thing, so you couldn't just do that with the problem the way it is right now. The tensions in the two ropes that are tied together would not necessarily be the same, because it would be like a third leg off of the rope. It's sort of a different thing. Yeah. Okay, so let's start figuring out these coordinates. So I'm going to put my origin at D, just like it is in the picture. And then let's see, X, Y, Z. So
Using the right hand rule, the positive z direction would be kind of to the upper right direction, right?
it would be to the lower left. And if I hadn't cropped the picture the way I did, you would see the Z over there. So I made it a little harder than the book made it, I guess. But yeah, the Z-axis, positive Z, has to be to the lower left. Okay, so where's the point A? So come back. So A is 140.00. B is 120.00. C is 72.00. So far, they've been pretty easy. D is the origin. E is 10 inches in the positive Z direction from B. So that's 120, 0, 10. F is in the negative Z direction from B. So that's 120, 0, negative 10. G is from the origin just 136 inches in the positive Z direction. So that's 0, 0, 136. H is 100 in the negative Z direction from the origin. So 0, 0, negative 100. And then I is 48 in the positive Y. And I'm going to put my about point, since it was a lot of work to get these coordinates, I'm going to put my about point at D so that these are also the row vectors.
Is it not 44.8?
Yes. Okay, so I'm going to put my about point at the origin. And so that says that these are the row vectors at these points. And now I'm going to draw the free body diagram. And now let's start putting forces together. So it looks like we're ignoring the weight of this thing. We have 140 pounds here. And we have, so let me first do the joint with the wall. That is a ball and socket joint. It says that. And so a ball and socket joint
Just for the translational freedom.
right.
However,
That's right, exactly. So it's just 3 components of a force vector. So I'll call that R. And then we have a cable force this way. I'll call that TG. And then I am going to, okay, well, am I going to do this? I've already drawn my free body. We could simplify things a little bit if we included this part of the string in our free body, because then we wouldn't have to deal with the 2 force vectors, the one going from C to F and the one going from F to C, because they're internal.
we also include the bully.
Yeah, I sort of always, I think of including the pulley also. So,
Through the free body.
so let me let me redo this. So, okay, this side is easy. That one doesn't change. But over here, oh. Okay, so over here I'm including the pulley. And I'm including the pulley over here.
Or you leave
So it looks-
you leave a gap there, or would you just have it? So,
Either one's fine because there's no forces acting in there. I just left the gap in there so you could see all what I'm sort of including, but your free body can be anything that you could wrap an imaginary three-dimensional surface around, you know, a closed surface around. So this is perfectly fine. And now we have, okay, so we have the 140 here. We have the ball and socket forces here. We have TG here. And then maybe let me just call this T1, since the second one is sort of complicated, what I would call it. And then this one, now we don't have to deal with the forces between those two pulleys because those are internal. We just have TI, or let's call it T2 here. And T2 here. Those are the same because that's all one cable. All right, and so now I'm going to start filling out the table. I'll start with R. Row vector is 0. Force vector is Rx, Ry, Rz. Cross product is 0. Then I'll do the 140. That is at the point A, so that row vector is 140, 0, 0. The force vector is 0, negative 140, 0. Cross product is uh, 19,600 negative in the z direction. Then I'll do T1, the row vector. So that is at the point E, so 120, 0, 10. Now we have to figure out that force vector. And so for T1, a vector in the direction of this cable is G minus E. So 0, 0, 136. Minus E, which is 120, 0, 10. And so that's negative 120, 0, 126. Then a unit vector in that direction is negative 0.690, 0, 0.724. So the force vector is this unit vector times T1. So that's negative 0.690 T1, 0, 0.724 T1. And then the cross product so 120, 0, 10 crossed with negative 0.69, 0, 0.724. And we know that the answer is just going to be multiplied by T1. So I got 0, negative 93.78 T1, 0. And then I'll do the T2 that goes to the point I. So it acts at the point C, 7200. So we're going to go, the vector in the right direction is going to be I minus C. So that is 0, 44.8, 0. This is our vector in the direction. Minus C, 7200. So negative 72, positive 44.8, 0. And then our unit vector in that direction
But why'd you do 0, 44.80?
because
Oh, that's I.
that's I, yep, minus C. Because we want a vector going from C to I. And so this is negative 0.849, 0.528, 0. So that force vector is that unit vector times T2. Positive 0.528 T2, and then 0. And then the cross product is 0, 0, 38.02 T2. And then, so 1, 2, 3, 4, 5, 1, 2, 3, 4. So the only one left is the T2 that goes to H. That acts at the point F on the body. So 120, 0, negative 10.
Wait, is it saying the whole length of that is 10, so would it be half of that?
No, it's saying each one of those two,
Oh, each one of the two lengths is 10.
right. Okay, so now a vector in the direction we want goes 2h from F. So 0, 0, negative 100. Minus F is 120, 0, negative 10. So that's negative 120, 0, negative 90. And the unit vector is negative 120, 0. That is negative 0.8, 0, negative 6. Negative 0.6, sorry. And so the force vector is negative 0.8 T2, 0, negative 0.6 T2. And that comes out to be 0, 80 T2, 0. Okay, so there's our table. And I think maybe let's stop that one there, because all you're going to do now is just the same thing we do in 2D problems, 3D problems. Add up those force vectors, set them equal to 0. Add up the moment vectors, set them equal to 0, and solve the system of equations. One thing about this system of equations, by the way, that maybe you could potentially notice when you first do the free body diagram. How many variables do we have here?
6.
We only have 5 because 2 of them are the same variable, 2 of those force vectors. And so if you only have 5 variables, you can't have 6 independent equations. Okay, so if you notice that there's only 5 variables, then as you go, you might want to be thinking like, where are we going to lose one of these equations? Yep.
The moment for x.
Yep, exactly. So 0, 0, 0, 0, 0. And so the x moment equation just ends up saying 0 is equal to 0, which obviously doesn't help you solve a system. So we get 5 equations for 5 variables.
Professor?
Yep.
Also for this one, so it does ask us to use the SI units, right? So
Oh, it does?
what unit would we get from finding these? Like using it in...
You would get forces in pounds. It's because that's the...
Foot pounds? Or
pounds are force.
Oh.
So foot pounds are torques or moments. So yeah, all these answers would come out in pounds, and then you can just ask Google how to convert from pounds to newtons.
Or you could do it the other way around. That would be fine.
Yeah, yeah. I didn't see that about SI units. It's about 4 newtons per pound, I think. Any questions about that one? So now we're going to do, was it number 11? 12.
Professor,
Mm-hmm.
in like a place where the gravity isn't Earth gravity, what happens to the pounds? Like, do you say something
Okay,
weighs
so-
or weight?
Yeah,
versus
so
mass?
it seems a little confusing because we tend to think of pounds as a measure of mass also. But pounds just aren't a measure of mass, and that's just the end of it. So so there's no problem with gravity or anything. You look on the scale and it tells you pounds, and that's a force. But yeah, I think we're all just screwed up because our bathroom scale has a conversion from pounds to kilograms, but those aren't the same thing. It's that conversion that's assuming that you're on Earth, Like the bathroom scale can't measure your mass. It can only measure the force you're applying to it. It can only measure newtons, right? So if you went to the moon and used a bathroom scale, it would tell you correctly how many newtons or pounds of force you're applying to it, but it would guess your mass totally wrong. Okay. So here is one where it's like so that F is an applied force. And we're going to calculate all the other forces in terms of that F. Okay. So we're going to have F in all of our answers. And if that F is 100, these forces are something times 100. If this is 1,000, these forces are that same thing times 1,000. Okay, so that's what we're going to get is answers that have F in them. Okay. And what else can we say? There's a little complicated geometry in here that we have to figure out. So let's first start again by just coming up with the coordinates of all these points. Notice this uses different X, Y, and Z orientation for your viewing pleasure. The A is going to be the origin. And I'll use that as the about point too. Why am I going to use that as the about point? That's true. Yes, then the coordinates will be the row vector, exactly. Okay, so the point B is 0, 10, 0. The point C is, so that is -4 for X, and then 0 for Y and 5 for Z. The point D, there's no D. Oh yeah, is, so that's going to be +4, 0, 5. And then E, okay, so now let's think about E for a second. If we look at this from the side, here's what we see, okay? So this is 10. This is 5. The point E is here. And this is 2. This whole thing is 10. Okay, so notice that this little right triangle and that big right triangle are similar triangles. You know, they're using that same angle over here. And so since 5 is half of 10, the height of this little triangle has to be 1. So that's the SAT problem that sneaks into this. But so now that we know this, we can figure out that E is equal to, so that is 10 minus 2 is 8 in the y direction, 0 in the x direction, and 1 in the z direction. And then I'll call F the point where that force F is applied. So that is just 5 feet in the positive y direction, 0, 5, 0. And now we're going to draw the free body diagram. And there's one thing you have to think about here. So how are we going to treat that? Okay, one thing you have to understand from the picture, or you can't really do this problem, is that there's a separate cable that goes from B to E. That's its own cable. That's all it does. And then there's a different cable that goes from D to E to C. Okay, you just have to see that from the picture, or everything will go haywire.
From B to E and then from B to what?
From D to E to C. So the one that goes from D to E to C is the one that rolls through the pulley.
So there's a pulley at E.
Right. The one from E to B is just holding the pulley in place. And so we can decide whether we want to so basically we can calculate either the cable tension in our first step. We can calculate either the cable tension in the cable DEC or the cable tension EB. And then we'd have to do a second step to calculate the other one. And it doesn't matter which one you do. Let's I'm just gonna for now isolate the bar. So the cable force that we're going to calculate is the one that goes from between B and E. Okay. So free body diagram. So it goes like this. That's a ball and socket joint at A. So it's an unknown force vector. And then at the center, acting down, there's the force F that, remember, is not a variable that we're solving for. It's like a parameter that we're going to get our answers in terms of. And then a cable force T. And that's everything, because that second cable doesn't touch the body that I've drawn to isolate. Okay. Once we calculate this force T, then we can isolate the pulley if we want to calculate that other cable force. So now rho, force, moment. So I'll start with R. The rho vector is 0, 0, 0, because that's the about point. The force is Rx, Ry, Rz. Cross product is 0. Then I'll go to F. So that row vector is 0, 5, 0. Force vector is, that's in the negative z direction. So 0, 0, negative F. And the cross product is negative 5F for X, 0, 0. And then the cable force, that acts at B. So the row vector is 0, 10, 0. And now we have to figure out the unit vector to represent that force. So a vector in the right direction. So we could do it as E minus B. Let's just do that. So 0, 8, 1 minus 0, 10, 0 is equal to 0, negative 2, 1. And then a cross product, a unit vector in that direction is, I should be able to think of what that is, but
2 over root 3 and 1 over, no, root 5. 1 over root 5.
yes. So that is 0, negative 0.894, positive 0.447. And so the force vector is this times t. So 0, negative 0.894 t, 0.447 t. And then the cross product.
So you can kind of just ignore the wire that goes from D to C.
Well, yeah, for this part, since it doesn't touch what I isolated,
Yeah.
I can ignore it for this part of the problem. But if we want it, eventually we'll have to figure out some way or other. Okay, so 0. My honest reaction, like if I saw this problem in a class, I would have done this part of the calculation and just figured that was enough and quit there. And so if you do that, I'll have to just grudgingly respect that decision. Okay, so this cross product is 4.47 T00. Okay, so that F in there screws things up a little bit. It depends on the calculator you have. If you have a TI-89 or an Inspire, you can put variables into your augmented matrix when you do reduced row echelon form, and it'll give you an answer that has that has it in terms of that variable. So you're in good shape if you have that. Otherwise, you probably just want to solve this by hand. It's not too hard to solve by hand because let's think of how many variables there are. There's 3 for R, 3 components. There's 1 for T. F is not a variable. So we only have 4 variables. Okay, let's make sure that we don't have 6 independent equations. Well, the y components are all 0 for the moment, and the z components are all 0. So for both of these, we have 4. So 4 equations for 4 variables. And so these equations say, Rx minus 0.894 t is equal to 0.
How's the x with the negative 0.894?
That doesn't make any sense. Thank you. Rx is equal to 0. Ry minus 0.894 t is equal to 0. And then for 3, Rz plus 0.447 t is equal to positive f. I'm just putting that on the other side to remind myself that's not a variable. And then the last one says, the fourth equation says negative 5f plus 4.47 t is equal to, and again, f is not a variable, so 4.47 t is equal to positive 5f and so that's not too hard to solve by hand. T is equal to 5 divided by 4.7 f. Let's do it. We got a couple minutes. Okay, so t is equal to 1.12 f. Rx, I guess I'll just do it as a vector. The x component is 0. The y component is f. And the z component is
Would you be writing this in terms of like f, so would be like
sorry, I'm at my maximum bandwidth right now. So I think you get this. And so you can see all those go, all those forces go up if you apply a bigger force F. Marco, did you have a question?
Negative?
yeah, something like that.
Probably.
And then still positive 1/2 and the component.
Yeah. So you got 1F minus 0.5F, so I think that's 0.5F. So I think that's right.
Yeah, so like 0, negative f, and then 0.5.
Any other questions? Yep.
If you have time, would we to look through the written assignment number 3 quick?
The what?
Written assignment number,
The weekly assignment?
yeah, we can.
Okay, yeah, sure. Number 3.